So, greetings and welcome to this talk on multiple acquisition context based deep learning approaches for magnetic resonance image reconstruction. My name is R. Sriprabha from Healthcare Technology Innovation Center, IIT Madras. So, magnetic resonance imaging is a versatile medical image scanning system covering a wide range of applications from simple injuries, spine, cardiac, musculoskeletal, neurodiagnosis to chronic degenerative conditions like cancer. It has high signal quality and it is non-invasive, unlike other medical image scanning systems like X-rays, where harmful radiations are passed into the body. The acquisition, this is the general MRI radiology workflow, wherein there are three stages. This is the acquisition stage, the post-processing stage, and downstream applications. The acquisition stage is the crucial part of the workflow and decides the quality of diagnostic decision making. Therefore, the context of this talk will primarily focus on the acquisition part of the workflow. Recently, meaning couple of years back when my mother was admitted for COVID, she had no risks on heart disease, diabetics or blood pressure. Yet she was asked to undergo 4 CT scans, which was invasive and harmful for her age. So, why is MRI the secondary preferred modality in practice? The acquisition, the adoption of MRI is however very far behind owing to its long scan time, typically from 45 minutes to even an hour. This is because MRI works by collecting radio frequency pulses using RF coils that are wound around large superconducting magnets that are placed in the scanner in a particular order, and there are multiple such coils around the scanner, the arrangement. And all these scanners switch intermittently, and this leads to what is called a repetitive time. And the repetitive time scales directly with the number of samples or measurements collected per image and the number of images per scan. So, this easily scales to 45 minutes to an hour. Another requirement is that the patient needs to remain intact during acquisition, and this leads to discomfort, especially when in the case of infants. Acceleration can be achieved to some extent by collecting less number of measurements. This is also called as undersampling, and however, when undersampling is done, it leads to aliasing artifacts in the acquired image, and a reconstruction step is required. Conventional methods for reconstruction are instance specific, and they involve nonlinear optimization solvers which necessitate repeated hyperparameter tweaking, and this increases the image reconstruction time. Therefore, our first objective is to improve the speed and quality of the reconstructed image. Recently, these deep learning methods have emerged, and unlike iterative methods, they infer an optimal parameter set, that is the weights of a neural network obtained by optimizing a loss function and using a training data set. So, we have tried several techniques in deep learning like attention mechanism to mimic the biological attentional modulation systems of biological neural networks, then deep cascading, iterative cascading, which is in order to mimic the iterative methods of nonlinear optimization, integration of classical signal processing approaches into the deep neural network, and using image features like image gradients, edges, gradient of logarithm features, and many more. And we have obtained promising image quality, and the aspects of speed are also achieved. And this was also deemed by the radiologists as very good quality. However, the radiologist also asked us another question: if these images or these approaches can be integrated into their workflow, to their scanner. This raised several questions, and a careful analysis of MRI data gave us the following insights. Magnetic resonance images are acquired by combination of scanner settings. Each combination is called as an acquisition context. For example, there are two types of contexts. Context could be continuous in nature or it could be categorical in nature. Continuous as in, it starts with anatomical details and a single tuning parameter called inversion time in the scanner leads to completely a different contrast. The utility of this is it highlights anatomical details, and this highlights abnormalities like cancers, lesions and injuries. So, every setting in this continuous parameter tuning is important and it is patient specific. On the other hand, we have different types of undersampling with different trajectories of undersampling, different amounts of undersampling, different anatomies and many more settings. From the deep learning standpoint, deep learning models are acquisition context specific, meaning they have to be trained for every combination of acquisition context. And this is because they suffer from this problem called overfitting, wherein they tend to operate effectively when the test data matches with the training data, and even when there is a small deviation in the acquisition context, they tend to perform poorly. This is also called as covariate shift or domain shift. And imagine in the workflow there are so many tasks, imaging tasks like super resolution, artifact removal, other than reconstruction, denoising, image to image, contrast to contrast translation, and this is going to lead to a proliferation of models. And as the number of contexts keep growing, this is going to pose a substantial career to thousands of clinicians and radiologists who often lack the machine learning expertise or the resources to train artificial intelligence based models at hospital workstations. On the other hand, we can take myriad acquisition settings, collect samples from wide range of acquisition contexts and train one single model. However, this model is still inadequate because a single set of weights of a neural network might not be adequate enough to explain deviations in clinical time, because such deviations in the data depends on patient and it is unknown in general. So, how do we minimize this gap between the diverse nature of MRI and the context specific nature of deep learning models? So, what we need to focus is not on the speed and accuracy, but also how to increase the throughput of these AI deep learning models and increase the adoption of AI based workflows in MRI. So, our motivations enlarged accordingly, that is to identify key limitations in clinical scenarios that warrant deep learning solutions, and accordingly design multiple acquisition context based neural networks and learning processes, and evaluate the scalability and generalizability to deviate at unseen settings in all these clinical scenarios. At the architecture, that is the neural network architecture level, dynamic weight prediction is the key, where different set of weights for a different acquisition context needs to be present in the network in a single training, and at the learning level, meta learning is the key. So, what have we achieved? About 2 orders of magnitude, where 200 trainings which may take months can be reduced to 1 or 2 trainings, which is just a couple of days. So, what is this meta learning? Meta learning is a learning paradigm, also called as learning to learn. It learns a strong representation, that is it learns a strong prior, and it learns how to learn tasks such that when new tasks come at inference time, it can adapt quickly. So, the best way to explain this is, it just not learns from images, it also learns how to adapt quickly. So, having spoken about context specific models and joint training, the proposed model here goes like this. Every data point is associated with an acquisition context, and we have in addition to a neural network, a lightweight auxiliary network called dynamic weight prediction meta learner, and the data point goes to a image reconstruction network, while the acquisition context information, which is an enumerated vector, goes as input to the dynamic weight prediction meta learner. It takes this context information and predicts context specific weights which are infused to the main reconstruction network, and flexibility is achieved. And in addition to scaling to a wide range of contexts, it generalizes to deviations in the acquisition settings, and when new data comes at test time, it can adapt quickly to the new data distributions, and also it can extend to new acquisition contexts without forgetting old context, that is active learning. So, as a first attempt, we just took a dynamic weight prediction meta learner and a simple neural network, and then the context information is passed as input here, and it predicts context specific weights which are directly copied to the neural network, and this is what we achieved. For example, this is cardiac context, which takes cardiac, brain context, brain acquisition information goes, and knee. So, according to this is a simple case. our first work on meta-learning, and it was scalable to a wide range of acquisition contexts in this case. There was another very interesting clinical scenario where the MRI scanner itself has this coils. It is just not one big large coil, it is several coils wound around the magnet at different locations to sense signals around the body, and this number of coils itself is a variability across scanners. And for instance, this is a 12 coil scanner, and there was a challenge recently that was advertised, wherein a 12 coil scanner was taken and several deep learning models were trained using, before that a set of subjects were scanned using the 12 coil scanner, and a data set was released and several deep learning models were trained using the 12 coil scanner. To the same 12 coil scanner, 20 more coils were added, it becomes a 32 coil scanner. Same subjects were scanned, there was no change in the data distribution, it is just adding number of coils, no change in the intensity levels also. But, and the challenge was that all the models that were trained on the 12 coil scanner should be evaluated on the 32 coil scanner. And it turned out that 30% of the images as deemed by radiologists tend to perform poorly in terms of reconstruction. So this is a very important clinical scenario because this is going to vary, because for a Philips scanner might have 12 coils, GE scanner will have 32 coils, we do not know, and the anatomy also keeps varying. And the amount of sensitivity of this coil also varies. Now, we took this clinical scenario and then we designed acquisition context vectors, wherein switching, and that is the presence and absence of various coil configurations were taken to drive the dynamic weight prediction meta-learner, and the context specific weights were infused into the main reconstruction network, and this gave us the scalability to a wide range of coil configurations. So this is one case. An even more extensive case is multi-contrast MRI, wherein the data itself needs to be interpreted carefully. For instance, what we see here is on the y direction we have multi-contrast MRI, wherein different types of contrasts are present, and within each type of contrast there are continuously varying settings. So every shape that you see here is not a data point, it is a data set. So each of this will have data sets. So and we took this contrast information as the feature vector to drive a dynamic weight prediction unit, and this is used to modulate the kernels of the base neural network. So the base neural network learns imaging operations, while the dynamic weight prediction learner learns all this context specific information. And we dive one level deeper, wherein at the learning level also the adaptive learning can be brought in, wherein each of these shapes is a data set. We just break it into two, the query support data and query data. Using support data, we adapt to each of these tasks, each of these shape is a acquisition context. We adapt to each of the contexts, making context specific models, and then take the query data, evaluate it on the support data adapted model, and then make one more level of correction based on query data. So correction, evaluation, again correction, two level optimization is done. This two level optimization is called gradient based meta learning or optimization based meta learning, and this is also one more level of thing that we have done. So let us see how this goes. For instance, the data is first divided, so we have 4 tasks here, T1, T2, flare and PD, 4 different contrasts. They are divided into support and query data, and after that we take a randomly initialized neural network that first adapts to each task. This is how. So for instance, it adapts to T1 data, bringing in T1 specific model, and then it adapts to flare data. So every arrow that we see here is a backpropagation correction. So then it adapts to flare specific data. Similarly, T2 specific data, proton density specific data, and this is called task specific adaptation or inner loop adaptation. This is only few gradient steps, it is faster adaptation. based on support data. So, next is after having all these task specific models, we take the query data, evaluate the loss with respect to all these query images, average out that loss, and then make one more level of update which is called meta weight update, outer loop optimization. So, this gives a set of weights called meta initialization. By way of this, I mean, it does not learn blindly from samples, it would have learned how to learn each of these contrasts, and then based on that makes one more level of update. So, this is another perspective of the meta learning. So, this is dynamic weight prediction network which undergoes two level optimization. This is main reconstruction network which performs image reconstruction, and then on a very high dimensional visualization, all these data points are separated well apart, and here the red arrow first takes the neural network which is the blue hexagon closer to each of these data distributions, and then from there two level optimization, gray arrow shown here and green arrow meta loop update is done. So, this enhances the scalability of the model, it increases the representational capacity of the model, and it is also computationally efficient because we are not generally this is millions of parameters are there in the whole neural network. We just take the lightweight meta learner and then do this two level optimization. And what have we achieved? So, we have been able to reduce this training to several orders without decrease, without expense in the accuracy. It adapts to a wide range of acquisition settings, it adapts quickly, and then it learns new context without forgetting, and it also tunes continuously to varying settings, multiple artifacts, different acceleration factors, different anatomies, and different undersampling levels. So, this is a quick summary of the models that we have developed. Context specific models are experts in their own context, but they do not have overall meta knowledge, or they cannot be tuned, and they are not storage efficient. Joint training it gives one single model, but their knowledge is inadequate. Dynamic weight prediction is both context specific and has an abstract knowledge, but it is also storage efficient, tunable, but its scope is still limited to smaller acquisition setting context. Dynamic weight prediction plus meta learning gives the advantage of all the tunability, expert knowledge, common knowledge, everything. So, it has the potential to learn very strong representations and pave the way for developing smarter MRI protocols for better patient care. So, there are